Physics chapter 29, theory video 6, decay graphs and equations. So now in the earlier situations we saw that the atomic nuclei emit radiation and become different substances, that is the decaying process. This decay is actually, if we draw it in a graph, you would see the graphs would look like this. So that is because this type of this pattern is called exponential decay. This pattern would be known as exponential decay, and the exponential means it is actually the half life is actually what is going to be affecting here. So if you take the half life is the of a t1 half is the mean time taken for half of the active nuclei in a sample to decay. So now if you can look at this graph, you will actually see why it takes this particular shape. So as you can see here, the sample percentage of undecayed nuclei reaches from 100, it reduces. So from 100 to 50, it has taken t0 to t half. So from 100 to t. So then from 50 to, for it to half, it takes 20, for 50 to 25, it has taken the same amount of time, as you can see. Then from 25 to 12.5, it has taken the same amount of time. So this is because of this half-life only, we say that this is an exponential curve. So this is a exponential decay, and that is something that we have already discussed earlier as well. Then this will continue, but this is not going to be a smooth curve. As you can see at the end of this graph, there is a little bit of it becomes a little bit unsmooth. That is because when slowly this will reach the end, when there are only a few undecayed sample, it because of the spontaneity and randomness, it might not become clearly smooth. We can if we take using this graph, if we take a certain equation to represent this graph, we can start with n0 undecayed nuclei. Then the number n that remain unchanged after time t would be given by n equals no e to the power negative lambda t. Lambda is the decay constant from the earlier situation. You can write this equation as, you might see that this written as n equals no exponential then negative delta t. Then if the decay constant is in per second, then the time should be in seconds. The symbol E represents the number E equals 2.71828. Just like it is just a special number, you need to know that it should be used. So this particular value can be found in your calculator, e to the power x button. You find the e value on your calculator, then you will be able to use it for this particular purpose. Write down a note on this. Decay graphs show an exponential decay because when the rate drops by half, the time remains the same. This is referred to as the half-life of an isotope. Put a star and write down half-life T1 half of an isotope is the mean time taken for half of the active nuclei in a sample to decay. Please draw this 29.10, then you will understand it better. Then write down. This graph can be mathematically represented by following equation. N equals NO e to the power negative delta t. So this E value should be obtained from your calculator, simple E value. Find that one and see whether you can use it. The values given here comma N0 undecayed nuclei, N number of undecayed nuclei left after time t, E special number 2.718, just like the special number pi, t is the number, the time in similar units as lambda. Lambda is the decay constant. Right. So now to determine the half-life of a sample, we can use this practical activity. However, we need to take something that is not going to decay within a second or two, but also it wouldn't take years. So if you take protactinium 234, which would decay by emitting beta radiation, beta negative radiation, so we can allow this to decay and observe using a counter. So what we do is, usually this will be provided to you in a laboratory in a bottle containing a solution of uranium compound uranyl 6 nitrate, and if you shake this bottle, you will be able to separate the protactinium into the top layer of the solvent, and then the counter will start measuring the decay of the protactinium. So if we measure the counts in consecutive 10 seconds over a period of few minutes, we will be able to draw a graph, and we can use that graph to obtain the half-life of it. So that is actually not much of a bigger deal and nothing complicated about it. It is just that we need to take a certain time sample and then get the values of get the number of counts for a period of time, and then draw a graph against time. Then the activity A, now we realized from the earlier situation that the activity A is proportional to the number of undecayed nuclei N. So we have a direct proportionality here because the activity has a exponential decrease with the undecayed nuclei. A is equal to AO e to the power negative lambda t. AO is the activity at time t equals 0. Then the activity after time t is A. When we take the count rate R in the laboratory, we usually take the corrected count rate. because the count rate is fraction of the activity. It is this count rate is also going to reduce exponentially with time. So R equals ROE negative lambda t, then RO is the corrected count rate at time t equals O. So here we can take an equation, common equation for all of them. X equals XO e to the power negative delta t, lambda t. X can be either activity, number of undecayed nuclei, or the received count rate R. So this is actually something that you will be able to understand through these worked examples. Suppose we start an experiment with 1 into 10 to the power 15 undecayed nuclei of an isotope, for which lambda is equal to 0.02 per seconds. Determine the number of undecayed nuclei after 20 seconds. So we write down whatever they have given here. And they have given the number of undecayed nuclei. So we can use the equation NO. So NO is equal to, we start at the beginning, we have NO equals 1 into 10 to the power 15. Lambda they have given 0.02 per second, and t has been given in 20 seconds. If it was given in minutes, you have to convert that into seconds. So we substitute it to the equation. N equals NO e to the power negative lambda t. So in here, instead of x, we replace it with n. Then we get, we use the EX button and calculate n. Then we will get 6.7 into 10 to the power 14. If you have any doubts, please ask. Question number 8. A sample initially contains 1000 undecayed nuclei of an isotope whose decay constant lambda is 0.10 per minute. Draw a graph to show how the sample will decay over a period of 10 minutes. So we have at NO, it is 1000 and lambda equals 0.10 per minute. So we can write the equation for this decay. N equals 1000 e to the power negative 0.10 t. Then we take data for this, because we need to calculate, we need to draw a graph. When it is 0, we have 1000. Then using the equation, we can figure out how much is left after 10 minutes. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we calculate how much remains, and using that data, we draw this particular graph. So I hope that makes sense. If it does, please do question number 16, 17 and 18. Then you will be able to understand it better. Now we are going to decay const. No, we will have to write a note on this. First of all, write down. Half-life of a sample can be detected using a isotope that doesn't take too less or much more time to disintegrate, such as protactinium. By using the data that we obtain to draw a graph, we will be able to find the half-life. The activity A of a sample would be directly proportional to the number of undecayed nuclei n. Therefore, we would be able to obtain an equation A equals AO e to the power negative lambda t AO is the activity at time t equals 0. If it is the count rate that we obtain, the same equation can be written as R equals RO e to the power negative lambda t, where RO is the corrected count rate at time t equals 0. As a result, we can obtain the key equation x equals xo e to the power negative lambda t, where x can be represented by activity A, number of undecayed nuclei n, O, received count rate R. Now we are going into decay constant lambda and half-life T1 half. So we know that an isotope that would decay rapidly has a short half-life. So it is obvious. If it decays at a slower rate, it would have a longer half-life. So the decay constant for something that is going to decay constant is the number of decays per unit time. So it is going to have if it is a rapid decay, then it is going to have a large decay constant. That is, the probability per unit time of an individual nucleus decaying will be high. So then what is the relationship between decay constant and half-life is what we try to figure out. If e to the power x is y, then x is the natural logarithm of y. Then in time equal to 1 half-life, t half, the number of undecayed nuclei is halved. So we can obtain the equation n equals NOE negative lambda t. So now in this particular situation, we are taking n upon NO e to the power negative lambda t half is going to be half. So you get the you get the mathematical portion here, which would give you the half-life of an isotope, and the decay constant would be inversely proportional to each other. That is going to be lambda is natural logarithm 2 divided by t half, which is going to be 0.693 divided by t half. So that means if we know t half or lambda, we will be able to calculate the other. Half-life and decay constant would have an equation that is going to be compatible with one another. Lambda equals natural logarithm 2 divided by t half, or natural logarithm 2 is 0.693 divided by t half. So that's another equation that you need to know. So that is the end of the lesson. Write down a note of this. An isotope that decays rapidly has a short half-life. That means its decay constant is higher. Therefore, they have a inversely proportional relationship. This calculation is not important. What is important is the final equation for you. Write down, half-life and decay constant are related as follows. Lambda equals, that is the decay constant, natural logarithm 2 divided by t half, 0.693 divided by t half. I hope that made sense. Do question number 19 to 22 and do the end of chapters as well. So we learned quite a few things here. Then we learned some equations also. Then the nuclear reaction can be represented by an equation like this that is given here. But you have to remember the conservation of A and Z should be remembered. Then mass energy equation delta E equals delta mc squared relates to mass changes in energy changes. That is also something that you need to understand. Then the mass defect is equal to the difference between the mass of the separate nucleons. We obtained the atomic mass unit, which is equal to 1.660 into 10 to the power minus 27, that is 1 U. The binding energy we discussed about it, that is the minimum energy required to break up the nucleus into separate nucleons. The binding energy per nucleon indicates the relative stability of different nuclides. If the binding energy is high, we knew that it was stable. The variation of binding energy per nucleon showed that energy is released when light nuclei undergo fusion and when heavier nuclei undergo fission. Because these processes increase the binding energy per nucleon, there would be more stable nuclides would be resulted. Nuclear decay is spontaneous and random process. So that means the count rates tend to fluctuate. So we have to obtain the average quantities, and we discussed half-life and isotope is the mean time taken for a half of the active nuclei in a sample to decay. Then we obtained a decay constant, that is the probability that an individual nucleus will decay per unit time interval. We got an equation for activity is related to the number of undecayed nuclei in the sample, A equals negative lambda n. Then the decay constant and half-life are related by the equation lambda equals ln divided by t half, 0.693 divided by t half. So then exponential decrease of a quantity with time t by an equation of the form we can get x equals xo e to the power negative lambda t. X can be activity r over the number of undecayed nuclei, count rate of the undecayed nuclei n. I hope it makes sense. Please do all the questions before you move on to the next video.